In our previous video, we have calculated the concentrations of hydroxide and hydronium, acetate, and acetic acid in a solution of acetic acid. We have used the Ka and we have applied the ice table. Let's see how different that is when the concentrations that you have when you have in solution is a base. In this case, we have dimethyl amino in here, so it's a 1.5 molar. And the question is, what are the concentrations in equilibrium, in particular hydronium and hydroxide? Let's see if we can figure that out. Well, let's set up an ice table. Initially, I have 1.5 molar. Notice that it's key to detect first that this is a base. All amino groups have a lone pair here that will accept a proton, therefore it behaves like a base. Initially, again, we will not deal with the concentration of water because we assume it's constant, and initially this will be 0, and you would say, well, there's already, if you're throwing this in pure water, there's 10 to the negative 7 molar of hydroxide, and we say, well, you know what, pretty much this is going to be almost 0, so we're not going to bother to carry it around. So in terms of change, there'll be a certain amount disappearing from the left and appearing on the right. And notice that in acids and bases, because each step is one proton at a time, the ratio, the balancing is always 1 to 1. You don't need to worry too much about it. So in equilibrium, you have 1.5 molar minus x, x, and x. Let's see if we can write the equilibrium constant. Equilibrium constant in this case is Kb, products over reactants. So I'm just going to write it B plus, for the sake of simplicity. Oh, it's negative, and this is my base. Again, this base is this dimethyl amino group. And this Kb is equal to 5.9 times 10 to the negative 4. Again, fairly small. Let's substitute it by our unknowns, x times x, and this is 1.5 minus x. We're going to approximate this again, as because the denominator x is going to be small enough because we have a very weak base, or not very weak, but weak enough compared to this 1.5 molar. So this is 1x squared, and this is 1.5. You may be asking, wait a minute, when should I not approximate this so that I need then to solve the quadratic equation properly? Well, if there is less than 2 orders of magnitude between your initial concentration and the equilibrium constant, in this case there is 4 or even 5, so if there is less than 2 orders of magnitude, you should not approximate it. But when there is as much as 4 orders of magnitude, you can assume that the results will not be that different. So let's see, that means that x is the root square of 5.9 times 10 to the negative 4 times 1.5. Okay, notice that the root square, this is going to be around 10 to the negative 2 molar. Okay, which is a fairly good approximation compared to 1.5. Okay, barely will tickle the initial concentration of the base. This is going to be, please substitute this into a calculator and get the real numbers, but the order of magnitude is going to be around 10 to the negative 2. This is going to be the concentration of OH negative equal to the concentration of my base, sorry, the conjugate acid. I guess I'm writing it now. Okay, so this is the concentration that I will have in solution. What is the concentration of hydronium? You would say, well, wait a minute, this is a base. I did not add any hydronium. Why should this be even involved? Because if you're adding some hydroxide, this will automatically change the concentration of hydronium because this all takes place in water, and one is modified because of the other. So notice that Kw will be, so sorry, let's put the numbers, 10 to the negative 14 divided by whatever this value is. Okay, around 10 to the negative 2. Let's just write x. So yeah, at home you can substitute the calculator, but notice that if this is around 10 to the negative 2, this will be around 10 to the negative 12 molar. Around 10 to the negative 12 molar. Okay? So now, how would that change if you have a very, very weak acid? In this case, why do I say it's a very, very weak? At what point should we consider an acid neutral? Well, the moment your Ka is smaller than the Kw, the 10 to the negative 14 provided by water, it means that this specific acid, so weak acid, that will provide hydronium ions even less than water itself. So it will not change the concentrations that much. So even if you were to do the calculations, so you say initially you have 0.5 in equilibrium, so let's say that this is pretty much 0, and let's see if that's true. Negative 5, negative x, negative a, plus x, and plus x. So in equilibrium, 0.5 minus x, x and x. Notice that Ka, even if you substitute it like that, and this is 10 to the negative 16, you will see that your x, if you apply the same calculations, you will see that your x is around the root square of 10 to the negative 16, which is 10 to the negative 8. Wait a minute, you just said that this is going to be 0 compared to how much the acid was going to be. So now it turns out that it's not really 0. That this acid provides 10 to the negative 8 molar of hydronium when initially there was already 10 to the negative 7 because of, so this would come from the acid, this hypothetically acid because it's not really acid, and the other one would come from water neutral. Oh, wait. It would come from the neutral water that was already there. Let's call this water. Okay. In other words, that the amount of hydronium ion that a weak acid with this small equilibrium constant, the amount that hydronium ions it contributes to water is even smaller than water itself. Okay, so this means that we can consider this a neutral compound because it does not change or quantitatively change the concentration of hydronium ions. Take home message: if your Ka is smaller than 10 to the negative 14, consider that a neutral compound. Likewise, if your Kb is smaller than 10 to the negative 14, that is not a base either. This is considered a neutral compound. Okay, we will see some examples of that, mostly for the conjugate bases, the conjugate acids of strong acids and strong bases, respectively. But that should be in your memory so that you remember when we talk about it again.